Hi and welcome everybody. Hope that you enjoyed the lunch. We are here to listen to Martin Skarsaune talking about Java compiler. Give him an applause.
Thank you, Nick. I was a bit concerned after doing a compiler talk right after lunch on the second day, but this is above all expectations. So as I said, my name is Martin Skarsaune. I'm a developer based in Norway. I'm just your regular Java developer, really, so you don't need to fear that I'm one of these smart guys that were at the VM Tech on Monday. This, at least I found surprisingly easy to get into. And so the question is, with all this cool stuff going on, why would you study more about the compiler? And I think, any piece of software that we rely a lot on, it doesn't harm to see a little bit about what goes on inside. And especially for my part, I mean, you can debug, you can read articles and things, but sometimes it's good to have a look at what goes on inside. So today's message is sort of threefold. I hope to achieve three things. I think the most useful part for your day-to-day work will be to look a little bit at what the compiler does to your Java code. And then we will have this crazy experiment to make a pretty drastic change to the language, which I'll get back to. And then finally I will show that something called annotation processors and compiler plugins, which if you want to do something with the compiler, that is the cleanest and best way to do it. So you can actually hook into the process without modifying the compiler as such. Now, I'm painfully aware that some of my countrymen entering Sweden don't know how to behave. I'm not sure if you place me in this category after the presentation. I'll be safely on my way this afternoon. If you don't read Swedish, it means that the standard response is to ramp up the police and close alcohol sales. Also, before I forget it, I'm part of the Java community in Norway, and we also have a conference in the fall. So why do I mention a conference in September now? The reason is that we open our call for speakers on Monday. So if you have something you would like to share, you should stay tuned. If you're not comfortable speaking English, we will accept talks in Swedish. We also have lightning talks of both 10 and 20 minutes, so you can check it out. A special thing this year, maybe for the more of special interest, is that we also have a contest to make the next promo video. I don't know if anybody has seen any of the JavaZone promo videos before. Usually get a bit of attention. So that could be you if you have talents in that area. So, I mean, these days we've seen lots of exciting things about Java 9, Java 10 and what goes on. But I guess some might criticize that perhaps the language lacks some features when it comes to doing proper spaghetti code. So we intend to see what we can do about that, and how do we do it, or what do we want to achieve? Well, we want to introduce this new syntax, so you can say goto and then a target statement. And at runtime, this will then make the program jump to that location, if you're unfamiliar with the term goto. Some other semantics, since this is a compiler, we want to validate that the target actually exists and give a compilation error. And we also want to see if we can detect that you're getting into an indefinite loop here. So how are we going to achieve this? Well, I guess you heard a lot through this conference. You have something called OpenJDK, this open source Java implementation. And in the subfolder there, you will find the source for the compiler. And a bit to my surprise, perhaps, because when I was in school and later, I had my encounters with grammars and parser generators and that, and I have to say it's It was perhaps a bit mixed experience, but what we'll see today is just plain Java code, and at least I found it quite straightforward. So we will then hack on the source code directly to support gotos. So about halfway through the presentation, we hope to be able to make this little snippet run and see what it does. So maybe before we proceed and head out into this unfamiliar territory, I should probably point out that, I mean, some of the debates we had in Java is just peanuts compared to what we're getting into now. So, for instance, Dijkstra felt he had to express his concern in a letter to the editor, and also states that the quality of programmers is a decreasing function of the density of goto statements in the programs they produce. So if you sort of derive a very simplistic this function, like a percentage distribution, where I take the amount of gotos divided by the total lines of code, I think in my quality will at least decrease 30–40%. So luckily my company is employee owned, so I assume I will be able to return to my job. So if we start with the real basics, what is a compiler? Well, a compiler is just a converter from one format to another. So in Java case, that would be some Java source code, and the output will be Java bytecode in the form of class files. Pretty sort of textbook architecture of this is to separate between what relates to the programming language that's the input, specifics there, and what deals with particular things with the target platform. So if you're doing a native compiler, this seems pretty obvious, right? Whereas in Java, we'll see that there are actually many stages, and they form a sort of pipeline so that the output of one stage will then form the input of the next stage. So the presentation will sort of loop through this, and we will look at our example and also look at other interesting stuff. So first we need to parse. So we have this string of characters that forms the input, and we want to make it into something more high level. Now the first step of parsing is normally called scanning or lexing, where we will take the characters as such and convert them into some more well-defined tokens, so we don't need to do string manipulation and that sort of thing later in the process. So I'll show how this works in our case. And fortunately, goto is already a reserved word, if you didn't know. One could wonder why they decided to keep it, so but at least that serves us well. And the way they have done that to give you a compilation error is actually the same as they do with other keywords, so it's actually already defined as a token. And so if I try to run the scanner on a source string like this, it actually works. And this is not the Java util scanner, it's a scanner class in the compiler. So I can ask for a token and actually verify that it is of type goto. Then I can take the next token and verify it's a valid identifier, and then I can see that it's terminated. So that part works out of the box. Important concept in compilers is an abstract syntax tree. The term abstract means that it should represent these concepts without being too closely tied to the language. And I think this is a simplified diagram, but I think just based on your knowledge as a Java developer, it should make sense that you have a compilation unit, that's your source file normally. You would have one or more class definitions in there. You would have 0 or more fields. You would have 0 or more methods. The methods would have a signature, and if it's not abstract, it would have a body. Within the body, you have all sorts of statements. So, and also within this process, the visitor pattern is extensively used. So if you're not familiar with the visitor pattern, it is a sort of callback mechanism where you get specific callbacks for each kind of object. And this is really good because the structure can be quite large and complex, but if you're only interested in one thing, you only need to deal with that. So you will get a specific callback for different sorts of objects, and as we'll see later, our goto will then have a dedicated callback. So in this case, we do a quite drastic change to the syntax. So we have to introduce a new type, both interface and implementation. And there are then, since it's a new type, we need to extend lots of visitors with specific callback for gotos. I will not cover all of them. There's one very nice one there called pretty, which is able to take any node and print it back to Java, which is very easy to get an overview and read. And that's actually what I used for the rest of the presentation when I show what goes on inside the compiler. And then there's two mandatory ones, which we just leave empty. And then I also, just to make the presentation easier, it's a helper object that basically keeps track of these references in all directions and in order. Yeah, and I extended the labeled statements to deal with this. So that's quite a lot of boilerplate just to introduce a new syntactic element in the language. And then there's actual parsing. So it's in the parser, it's a huge switch statement, and we just add a new case, and so it's the goto is already taken care of. We go to the identifier, and then there's some pretty cryptic stuff here, but it basically just instantiates one of these nodes, and we terminate the next semicolon, and that's it. So we could have a little look at what it looks like at this moment. So, for instance, if I was to run some goto code in just a plain Java compiler, we get a lot of these errors. We get 2 errors actually for each, saying that the parser can't deal with it. So if we then just load this code, probably not readable, but it's not that important. So if we load the new edition of the code, we will see that we don't get these errors anymore. We could even try to debug the code, but we will see that it doesn't really do anything. So we get this gibberish here. So if we return to the compilation process, so that's more or less the parsing. Then we have what's called enter trees or enter, which is the second phase. This is basically just high-level sanity testing, such that if it's a public class, that it's in the correct location, whether the class is already on the source path. And as we will see through the process, there's checking, but the parse tree is gradually refined and enriched. So for instance, here is, in Java, if you don't have any constructors in your class, it will insert a default public constructor for you here. That's what the compiler gives you for free. And then we have what's called process or process annotations. This is a typo there, I see. It's a standard API, which is now part of the standard compiler. So you can hook into this to create your own processors, and we will see an example of that near the end. There are also some relevant command line switches. By default, you will have, it will compile to bytecodes, but it will also use any processors that are declared. You can alter this behavior by saying that you don't want annotation processing, by saying proc :none. Or if you're only interested in dealing with annotations, you can use javac to run annotation processing and don't compile the code. So we'll see more specifics on that. Then we have the attribution phase, and this is where the bulk of the errors will come. So this is then basically lots of semantic checks to see that all the stuff you reference is defined, it's visible, you're allowed to access it. yeah, all sorts of type checks and these things. And also here we see that there's a correction here. It will add a call to the superconstructor in your constructors if you don't have a supercall. So in our case, we want to detect these sorts of problems, that you try to go to something that does not exist. And then we simply, what was previously a empty implementation here, we just use this helper object to see if we can find our target statement. If we do not, we simply say that we want the compilation error, and for this error there's actually an existing compilation error which is used for labeled continue and break, so we can just reuse that, and we're done. Yeah, that's how it's implemented by the scenes. I think I'll just skip, we can just see the end result in the end. Then you have the flow phase, which is also checks by the compiler, but this is not just static checks, but also things related to the analysis of the flow of your program. So for instance, if you have unreachable code, it will be detected. If you're using variables that are not assigned, it will detect it. That there is a return or exception thrown from your method. It also figures out a final and effectively final locals. So you do not break the final ones, and that whether they can be effective for lambdas or not. And also with checked exceptions, they will see if that makes sense. The things you catch, the things you throw, and so on. And so we would like to give a warning if someone tries to put up gotos in a combination that would get us into trouble. And then we have just a helper code for that. And in this case, we create a new compiler error. I think I'll also skip that. Then we leave our experiment and look at the more interesting stuff, I think, for most developers. So we have what's called the desugar phase. And if you recall Java 5, there was quite a lot of talk about syntactic sugar, and what that means is it's something you can express in source code, which gives better expressibility, but it's actually implemented in an old-fashioned way behind the scenes. So for instance, the comparator interface was made generic. So if I wanted to create a comparator for integers, pretty silly, but if I wanted to do it, then my compare method should take integer arguments, right? But this phase here, this subphase called transtypes, is where we usually refer to erasure, that the generic information is not relevant anymore at runtime. So here we are in a situation where we have a compare method with two integer arguments, but it's used as an ordinary comparator. And this will give us problems. Does anybody know what the compiler will do in this case? It will, I'll answer myself, it will insert what is called a bridge method, and it's marked as synthetic. Synthetic is something that is a flag to say that this does not come from source code. This is something the compiler did. So it will actually create a compare method with object arguments, which in turn calls the real compare method. Now, if you have been debugging or looking at stack traces, you may have seen examples of this, which at least used to confuse me. So here we see both a stack in the debugger, and we see a stack trace that refer to line number 1. And this is then this bridge method that occurred out of nowhere. You have some tool support for filtering out synthetic ones, but they are still there at runtime. And this is also, as you know, in Java, you can implement a class within another class. So here we have an outer class with a private method foo, and we have an anonymous inner class that calls this foo method from the run method of a runnable. And as you may have noticed when you're looking at class files and such, the compiler will extract this implementation and place it in a separate class with a generated class name. Since this is an anonymous inner class, it needs a reference back to the enclosing instance. So we see that it has a field for the outer class and a constructor which sets this up. And then when we construct it, we'll then instantiate it with a reference back. All well. But now we see here that now this inner class is just another class in the same package, and it refers to a private method in the other class, which is not legal. Has anybody seen how the compiler will deal with this? Here again, we have then a synthetic method, which is called an accessor, which is there simply just to provide access to the private method. And you see the synthetic method has package protection, so that's okay. And you may also notice this if you're reading stack traces or debugging, that you may get these access $something methods appearing. So that's another example of something the compiler does. Then we have a lot of other desugar stuff. So I put quite a few of them here. Here we have a number of Java 5 syntax things. For instance, the asList method is, yeah. Well, if you do Java P, you can see it. Most decompilers will be quite clever in inlining synthetic stuff. But so what I did for this presentation was I was debugging and just looking breakpoint and seeing the structure as such. So that's how I found the answer, so to speak. So arrays asList is a generic method, so it requires objects, but here we give primitive arguments, and so they have to be boxed or auto-boxed. So it will then insert method calls to turn these primitives into proper objects. Then we have also unboxing. You see further down in the loop, there is a boxed integer which is used in a computation. And there it will then insert a unboxing operation to turn it back into an integer. So sometimes if you get these null pointers out of nowhere, it could be an unboxing going on. Because if I was null, of course calling int value on it would give us a null pointer exception. Furthermore, asList is a var args method, but there is no such thing as var args at runtime. So this is then done by putting all the arguments in an array and passing that to the method. We also have a for loop here. And you may recall a for loop is created for, you can use it either on arrays or instances of iterable. And an iterable needs an iterator. So it will create a synthetic variable for the iteration variable, assign it an iterator, base the loop test, the loop condition on the hasNext, and it will retrieve the next object through the iterator, and it has to make a cast here because the generics don't apply at runtime. Also, enums came in Java 1.5. You will feel that, okay, enums have very compact, nice syntax. So here we have an enum with 3 valid values. But it's actually, and you've seen that you get a lot of functionality for free with enums. That's also something the compiler needs to take care of. So it will create a constructor, so we can have proper objects which are type safe. To save some space, I haven't elaborated it, but it will then assign proper objects to these fields. You also have the value of, which needs to be cast so you get the type you want. And we also have the keeping track of the fields and providing an accessor to it. So all of this is inserted during compilation. And then there's a thing that looked really bizarre to me at first. Of course, you can use enums in switches, but switches are only for primitives, right? So what did I do to achieve this? If you decompose a class file, you will see something quite strange looking here, because this is the thing that it switches on. So it creates a custom class just for this case, and the class contains a int-to-int mapping table with a rather cryptic name. So when this static is initialized, it will be with just default values. Then there's a static block, and it will take all the values that you have used in your switch statement and populate this mapping table with the corresponding number. And then we can see that it can then use that number in each case. Now, does anybody have any suggestion for why the compiler goes through all this trouble? Couldn't it just use the ordinal of the enum directly? That was my first thought, at least. Yeah.
Because that might be in a different jar, right? You might have changed the enum, so those numbers are not necessarily known.
Yeah, that is correct. He said the enum itself could have changed in the meantime. That is correct. So because this static block will then be run at runtime, whatever the ordinal of the enum is now, and you even see if even if it's been removed, we catch the no such field error, so the switch would never apply. So it basically does this dynamically at runtime to deal with just that this is existing compiled code and the enum has been changed in the meantime. Yeah, so that's the most relevant things from dsugar. And then we go to the generation phase. Here still there's some more stuff done to the code. We organize initializers. Yeah, I will show details. String concatenation is handled here. And of course, the most important part is to do the bytecodes. So for instance, the constructor. So here we have a field that's initialized, and we have a declared constructor. We'll have a super call, and the field will be inlined into the constructor. And if you've been debugging, you will have seen that at runtime there really is no such thing as a constructor. It's a method called init. The same with the static stuff. Declarations are moved into block with any static blocks you have, and it's called clinit. It's a static method. Also, you can use plus operator, of course, for string concatenation in Java. There's no low-level operator for strings. So what happens here is it will instantiate the string builder. It will append the various parts and take it to string of it. This is also something you get for free, but this is what goes on. To save some time this time, I'm not going through all the specifics for gotos. It's not many lines of code. There is an existing goto bytecode that does exactly what we want. The problem is that everything is not intuitive, because we are sort of abusing the compiler to do something that it was not meant to do, and some logic in there. This is basically for if statements. So I left that part out. I will there's a reference to a video at the end if you want to get into the details. I thought that would save us some time. So if we then try to do this stuff, I will just get the latest code here. If we try to run our tests again, it should be green. Yeah, pretty much everything is in here. We can see that if you have circular gotos, we get a warning. If we try to go to something that does not exist, we get an error. And we can see the results of running our little application. So if you pay closely attention now, you should be able to see something happening here. So we just have two label statements here. We print something, and now let's see, cross our fingers here and say, "Whoa!" And we jump again, and up there, and we jump out, and we're done. So that's basically it. Yeah, so we seem to get where we want. Maybe it wasn't such a good idea, but we managed to get there. If this reference is too old, I provided some fresher changes that we'll just have to see how it turns out in the end. Yeah. So I would like to have a short look at lambdas, because that's an interesting topic. You may have read some articles about this, but I still think it's a very fascinating thing, what they did with the lambdas. Because it's a change to the language syntax, it has big implications for the compiler, but you will see there's quite a lot of it is deferred to runtime. So there's many things going on to let you write lambdas. And a very interesting solution they come up with. So if we have a really trivial lambda, again, a useless comparator, but to make it simple, the compiler will, you may have noticed while debugging that it will create a method for the lambda body. And big improvement over the static inner class that we just saw is that in this case, the lambda does not refer to anything of the enclosing object or its supertypes. So the method can be static, which is good. We don't have an object lying around that refers to something it doesn't need. So we have the various arguments. If you have captured final or effectively final, you get additional arguments for that, which is really nice while debugging, because you did not have that with anonymous inner classes. And we have the body inserted like this. And then, so that's the body, but then we'll see that in place of the lambda, we have some slightly more cryptic stuff. Now this, what's it called? Single abstract method interface that this lambda is supposed to be is a comparator. So there are it needs to fulfill a role. And so it's this invoke dynamic call, which I will get back to, needs certain meta information about this lambda. So it will tell the lambda it should implement the method compare of the type comparator, and the signature of the compare method is to object and returns an int. The actual implementation refers to this lambda method, and the actual signature is this one. And so if we take this lambda at runtime and just use reflection to look at it, we'll see something like this. We get this generated class here, which has a compare method for two objects. Yeah, and a private default constructor. And this is kind of interesting. If you have been debugging lambdas, you will have seen some rather cryptic stuff in your call stack. It actually then, at runtime, goes through something called a lambda meta factory, which receives this meta information we just saw. And the default is called an inner class lambda meta factory, which will implement it by an inner class and use a framework called ASM to generate the bytecode for that class on the fly when it needs to. And really interesting, and maybe I should say, why is it done like that? Well, the language designers, why couldn't they just do it at compile time? And the thought is that, okay, now we implement lambdas with generating an inner class. But perhaps in the future release of Java, there will be a more optimal solution, such as a function pointer or something. So the compiled code is not bound to the current way of doing lambdas, because you have this thing that's deferred to runtime, which could then, in the future, do something else without you having to recompile your code. And the same actually applies for if you try to serialize a lambda. It will be a sort of generic form of the lambda which just stores this meta information and any fields you have captured, which then goes through more or less the same process to turn it back into a lambda object. So even if you have a lambda and you serialize it today and you deserialize it sometime in the future, they can do the same optimization. That's pretty cool. So the question now is there anything we could do to allow running lambdas in older versions of Java? Is anybody in this room not on Java 8? Someone poor soul too? Okay, it's this used to be a more widespread problem. So we could of course capture the generated class, but since we're playing with the compiler today, it would be interesting because as we set up the call to the invoke dynamic, we actually had all the information we needed in order to create it at compile time. So there's a file called source in the compiler, which you can test for various properties of your configuration. So there's something called allow lambda, which is only available for Java 8 or newer, but we just say, well, 5 or above, because that was the oldest JDK I was able to get hold of. And then I add another test which says, well, do I have to do something special with lambda as well? If it's newer than 8, then I should. And in this unlambda phase where we set the invoke dynamic call, instead I will just implement this class on the fly and call that. So it will look something like this. I will just generate the name class and implement, and I show the bridge method, but I actually get that for free. So instead of calling the invoke dynamic, we just instantiate this thing instead. So yeah, maybe not the most convincing example, but I have then put this also into our hacks. So if I run a test with some lambda that is compiled and run, we can actually see that I can run it with Java 1.6, and it shows what the generated inner class looks like. You can also do comparison with what it would be in Java 8. This is not thoroughly tested. This is just like for demo purposes, but it just shows that they could have done it this way. They did it in a probably cleverer way, but you have all the information at compile time. Reference that does not really work outside Oslo, but we have this museum named Lambda, which the politicians have been arguing about from about the time when I was born. And this was a sort of way to get there. And actually looking out from my office now, it's on the way. So finally we'll get there. Okay, so finally I wanted to show a little experiment of the more proper ways to interact with the compiler for your custom needs. Maybe the example is not that good. The main thing is to show how it's done. So if you just ignore the top there, maybe I should say that the means to achieve this is an annotation processor and the compiler plugin. And what I would like to have is a way to annotate a method with a special annotation that says that instead of running this method, you should put in a invoke dynamic call, which will delegate to bootstrap method somewhere else. So you can play with invoke dynamic in plain Java code. So the annotation processor, actually seen quite a lot of references to this this services interface in Java. It's called SPI, service or something provider interface. Yeah, service provider interface, which means that in your jar file, if you deliver some artifact, you can, under meta-inf services, put a text file called this JAVAX annotation processing processor, plain text file, and inside there put in references to any annotation processors you have. And this is really cool because say you're delivering a library of some sort which heavily uses annotations. This will then, and you want to give some compile time feedback of maybe your user used your annotation in the wrong way. This will then just be part of the compilation process unless they explicitly tell you to get out of the way with the command line switch. So this is quite neat. And then this is quite straightforward. I've simplified a bit. You need to extend from a abstract class. You need to say what kind of annotations you're interested in. The latest Java source version you support. You have to implement a method. And in there you would typically look through the source for annotations. In our case, we will first make some tests on the setup of the compilation, that's correct version of Java and so on. And then if we have then that is okay, we will do various checks on whether the reference in the annotation was correct, whether the class exists, whether the method is public, and so on. One little caveat here is if you are creating, you have a code base which includes a compiler plugin, you have to specify that it should not run annotation processors while compiling itself, because it's on the class path, so it tries to do it, but still it's not yet compiled to get into catch-22 there. Yeah, and then we go to a more powerful and advanced thing called compiler plugin, which allows you to do more than annotation processor. So here again we can hook into the process that we have become familiar with, and I will show you how you get these events back and allow you to interact. And here you would typically make changes directly on the abstract syntax tree. Annotation processors are more useful for giving error messages, static checks. Here you can basically do anything. So again, there's a file that you need to put in the services folder, which refers to your plugin. And here is a few more steps than we just saw. Here the plugin needs to get a callback to an init, and a typical thing you would do is to insert what's called a task listener, and it must declare a unique name. And then the task listener in turn is the one that receives the events from the compiler. So you need to implement this method, and so you will then get feedback throughout this compilation process you see at the top. And the tricky thing then is to decide where you want to intervene, because I said the compilation will gradually refine the structure, so you must make sure that all the information you need is there. But also, if the changes you've done must be picked up by something later, it has to be before that, or you could do it in several places. So in this case, we defer it all the way to the generate phase, and we have this method that basically just meddles with the method references for calling methods and does invoke dynamic instead. And here there's a requirement for the users of your library. For the annotation processors, they were just included and they didn't even know about it. In this case, you need to specify explicitly that you want this. So actually the annotation processor will verify that this is included, so you do not attempt to do this without having the plugin included. So, but if you have some sort of application-specific need of some sort that you would like the compiler to take care of, this is the way to do it. Yeah, so I don't know if demo says that much, but at least we can compile and we can debug. So we have, if we look at the main method here, we call the do stuff on some service, which has then this annotation. We see the code does not go here. Instead, it goes through some rather JVM internal cryptic stuff and ends up at our bootstrap method here. And that in turn will return a method reference, which simply delegates another method. And we also see here in the code stack that something funny goes on. So here we could do whatever we liked. So this method would be, you would be free to do whatever you like there to substitute that method. I should perhaps also show some output from the annotation processor that you would get. Yeah, some things that you have to use the plugin. The method must be public. Can find class. Blah blah blah. This is typical things you can do in this case. So yeah, that's more or less it. To wrap up, Java compiler is written in pure Java. I mean, there are advanced parts in there, but lots also quite straightforward. Compilation occurs in many phases. Programming language advances, like we've seen these days with the modules and also other changes in language, require good support from the compiler. It's an important part of our ecosystem. Lambdas are compiled in a forward-compatible manner, and annotation processors and compiler plugins, you can use them to tailor your compilation process, do something really powerful. Some resources. I have uploaded slides both to JFocus and SlideShare. Of course, as you may have heard in other money talks in this, OpenJDK is something to look at if you want to learn more about Java. There is a more tutorial-like compiler hacking. The sample code today is the code that uses it. I talked to the Oracle guys earlier, and they said there was no problem publishing a fork if anyone for any reason would want Java with goto. But I have to do a little preparations before I could do that. Slide pack. Also for the bytecode thing, there's a bit longer talk from Devox if you're interested. Yeah, I think we have 3 minutes left or something.
Yeah,
So
I think we have 3 minutes left.
Any questions or comments?
Raise your hand and I will run to you with the mic. I think everything was clear.
Okay. Well, in that case, I would really thank you for coming.